Hello, my name is Dan Lee of CUNY Graduate Center in Queens College, and I will be giving a mini course on an introduction to general relativity and the positive mass theorem. So in this short video, I'll just be giving you a quick rundown of the topics that you should expect to see in this series of videos. So I plan to start at a very elementary level. So we'll begin with just a discussion of space-time geometry and the Einstein equations, and we'll discuss the essential example of the Schwarzschild spacetime. From there, I'll give a brief discussion of black holes and talk about the important concepts of trapped surfaces and marginally outer trapped surfaces. And then from there, we'll discuss the constraint equations and initial data sets, with special attention to asymptotically flat initial data sets. So asymptotically flat initial data sets is essentially the setting of the positive mass theorem. So the positive mass theorem, of course, is a famous theorem that goes back to the work of Shane and Yao and Witten. But in this series of talks, I'll be focusing on a proof that is in a joint paper of mine with Eichmeier, Huang, and Shane. And in this proof, so the proof of the positive mass theorem breaks down into sort of maybe two main pieces. The first one, which is an important technical step, is a certain density theorem that allows us to reduce the theorem to the case where essentially asymptotics are better and where we have sort of better properties. So, I hope to discuss the density theorem a bit, and then I can talk about the actual theorem, which is a proof by contradiction, which involves sort of constructing a MOTS, a marginally outer trapped surface, inside of our initial data set that has some sort of contradictory properties. And for the final part of this series, we'll focus on recent work of mine, again with Lanshan Huang, on the equality case of the positive mass theorem. So in the equality case of the positive mass theorem, we have to show that if the mass is zero, then the initial data set should sit inside trivial Minkowski space. So it turns out that proving this is a lot more technical than one might guess, and I would hope to give you some of the flavor of how that proof goes. So if you're interested in any or all of these topics, then I invite you to watch the rest of this mini course.